Hi, everyone. I just wanted to mention this is my first time here and already excited to go through some of those couple of presentations early in the morning. I'm looking forward to the ones that come later as well, some really good ones there too. What I'll be talking about today with everyone is the digital beamforming, as mentioned in Ka band, and what are the challenges in this part. And let's dive in. Next. So just to give an outline on the presentation, the talk itself, I'll cover briefly, give a context on the trends that we are observing in the communication sector, what's happening. I think some of it was already touched upon by Dr. Williams earlier for Filtronics, and it's pretty much actually flows in a similar way of what's happening in the space on the connectivity and capacity side of things, how the whole space is evolving itself. And this emergence of the new space or the smart payloads that are coming about, the whole revolution in that space, particularly in the LEO constellation and the so-called mega constellations. And what role does Satixfy play in this emergence of the new space itself? I think that's where you get to learn a bit about the Satixfy and what we represent and what the work we are doing. Following that, we'll go into a bit into phased array technology itself as an intro, very brief intro. Most of us, I guess, are aware of what's the phased array antenna looks like and what does it do. With the focus of going into a bit of the digital beamforming, the advantages that it offers, which is the core technology for Satixfy, and the challenges that exist in this phased array technology in general. We'll take a couple of challenges out of that. There are quite a few of them, and that will be the focus of this talk a bit, which will be the phase noise and the jitter impacts, particularly when you come to high frequency applications like the Ka band itself, which is a millimeter wave. And look at a bit of the calibration challenges. I mean, calibration is a well understood thing. Phased array is pretty much synonymous with calibration. If you're building that many antennas with all the RF and all the other components, pretty much your life is calibration. And hence we'll take a couple of things inside that as well. Again, it's a big area, very vast area, and I'll touch upon a few aspects there. And then we'll sum it up. So over the last couple of decades, I would say, there's been explosive growth in connectivity and data consumption across the whole communication chain. I mean, we know that how the whole wireless communication as an industry has evolved. In my previous life, I was in cellular world, terrestrial communication. I moved into satellite communication, so I've seen the entire evolution happen on the terrestrial side up to 4G. And then, of course, beyond that was the 5G. But by that time, I had moved into the satellite side, and we saw how things are evolving there. It's been an incredible journey on the wireless communication. We started off with the wireless communication was actually, if you trace back the history, wireless communication started off together for both terrestrial and satellite in some way in the late 80s and early 90s. They both were pretty much competing for the same segment. Eventually, terrestrial outpaced satcom. But the goal was connectivity all throughout, getting devices, getting people connected. So it's the interconnection of everything was the one that was driving all of this. It started off with humans and devices first, became devices being connected with themselves, which led to this whole next wave of what's happening today with regards to 5G, 5G plus and 6G. It's not going to be just humans getting connected. Now devices are going to get connected. Which are billions of them. Everything's getting the so-called smart added as a prefix to it. So no longer it's the smart humans, smart devices, smart payloads, smart everything. And at the same time, the good thing that's happened is that the industry has realized that terrestrial cannot solve every problem. They cannot meet this global connectivity challenge that they had set themselves to be. We now see satellite has joined terrestrial communications and has become now an integral part of this whole communication delivery, which is now part of the standards. If you look at the release 17 onwards, release 17, release 18, release 19, all are focusing on NTN as the next wave of connectivity to meet this goal of connecting all of the humans, there are still a sizable population that's not connected, as well as try and deliver connectivity across the entire planet, not just on focused in certain areas where there's high density of population. We still have only 10% of the actual planet that's covered with regards to connectivity when it comes to the geography. So satellite communication now become a complementary thing, which I think is a big thing that's happened. And the two fundamental trends that are happening in satcom are the emergence of these mega constellations in the form of LEO, and the kind of sectors that are evolving within that space as well. There's a broadband service that is coming in, which are constellations directly providing high-speed applications to consumer at very low latency. So they want to. So satellite is no longer like a geo-only high latency system, which is only for a certain broadcast. We're now moving into a new space where satellite is competing, well, not exactly competing, but complementing the terrestrial. So your user experience is no longer going to be a dramatic fall as you move out of a terrestrial into a SATCOM network. So that's the goal. I mean, and the LEOs are fundamental to that. The low latency applications that will allow you to browse, do multimedia applications, require the system to be very responsive. You cannot have delays of hundreds of milliseconds in your system. You need to have very low latency in the system. Plus very large bandwidths as well, which are available in this for the broadband, especially in the KU and the KA bands that exist. There's another segment that's evolving as well, which is the direct-to-device. Again, this is interesting in itself, which is, I think most of the room is familiar with now the next generation handsets that are coming out from Apple, from Samsung and others, and in Android space, in iOS space, they all are supporting satellite connectivity on your handheld device. This is a completely new thing. It's never happened before. And it's all down to what's happening in the space now and what's coming up next. There are new news. There's a recent news in the media which I print, where how Globalstar has got an infusion of $1.5 billion for expanding their constellation. We are hearing about new companies that are emerging like AST, Space Mobile, who are trying to demonstrate their capabilities in the space and try to bring multimedia directly to the handheld devices. So as you can see, the whole market and the whole space is changing quite dramatically. And SATCOM is actually very much an integral part of this. On this slide, without going into too much detail, basically what I'm trying to show is a basic trend. So the terrestrial basically grew from a 2G all the way to 5G and beyond. Now they're talking 6G as well. The trend has been that the edge computing has become more and more smart. There's been much more things happening on the base stations that were initially being used just to connect to a device, providing just some sort of basic resource planning, into now into a high level of computation and resource management happening right at the edge itself, in the form of 4G, G Node Bs and the E Node Bs that were the evolution that happened in that space. Similar evolution now started happening on the satellite side. We started with the RF bend pipe system, which everybody's familiar for a long period of time, almost for like more than 2 decades. They started getting replaced by digital bend pipe, where again there was more flexibility and dynamic and moving the resources around in a more organized way. And now the new trends that's coming about with the new space, with the new constellations that are being launched, is the regenerative satellites, which is like a combination of all the other Node Bs that we talked about happening on the cellular together. We're talking about combining the E Node Bs and the G Node Bs into the satellite itself, which will start doing resource management, smart processing, using all your resources, particularly spectral resources, in the most effective way, so that your user links and your gateway links are being used in the most dynamic and the most efficient manner as possible. Again, all driving efficiency in the system. That's the main purpose of wireless communication and its evolution. Everything leads to a more efficient, every generation leads to a more efficient system and efficient use of the resources available. That efficiency and is basically means that essentially SATCOM is now, the payload particularly, is no longer just a simple reflector. It's doing a lot more processing. A lot more processing means it has a very high level of digital content now that needs to be injected into it. What does that mean? Basically, we're talking about bringing onboard processing. So now the payload is not just taking and doing a frequency conversion and pushing it down to the gateway, which does all of the processing. The payload itself now will have a capability of demodulating your data, remodulating it for a feeder link, or processing it for certain application, maybe even directly communicating with the device itself without going to the gateway itself. So it could be a direct link between a device to device through the payload. So there's a lot of different architectures that are being thought about, both from the 3GPP perspective, as well as from the actual implementation that are happening on various constellations like Starlink and the other ones that are emerging in future. So what we are showing here is different. If you look at this one, this is a special digital payload that Satixfy built for demonstration using some of our initial technology that we had developed on the ground. It was literally like a COTS commercial of the self, because none of these technologies that we had developed were actually meant for space. They were actually ground technologies, but we put a whole system together, hoping to demonstrate these capabilities, which had onboard processing using our SX3099 ASIC and our digital beamforming chips based antenna that we had developed for the ground, that we had repurposed it for the space. And we'd hope that this would be a good demonstration that went on with OneWeb as a host payload to demonstrate the future of this digital payload and what can be achieved. And the goal was it should just work for 6 months. It's been 24 months, nearly 24 months. The system is still operating on the system. This is commercial off the shelf. None of them radiation hardened. None of them designed specifically for space. It just goes to show what Elon Musk has proven as part of Starlink, that there is a market, there is a space, there's a part of the space which is quite conservative, has been very conservative for space applications. Radiation hardened is some of the very buzzwords, but actually commercial off-the-shelf companies are already working at a much higher quality grade that should sustain themselves in the space. With that in mind, of course, it doesn't mean that we just throw in COTS equipment, but essentially you want to bring in still some good practices, more radiation hardening, more redundancies built into your system. But what it goes to show is that the pace with which systems can be launched, the pace with which the systems can be designed, the whole cycle has really shrunk a lot. And the market is under great stress, as we heard earlier as well, from the perspective of applications and how fast you want to go from design to production. Space needs to evolve at the same rate, otherwise get left behind, just at the pace at which terrestrial markets are evolving. So Satixfy is basically quite integral part of the new wave that's happening. We are basically spearheading this whole digital revolution with the ASICs that we are developing, all in-house, which are targeting all these applications like onboard processing, bringing new features like beam hopping, and more importantly, the whole move towards giving a very high capacity system through the phased array antenna technology, which is our electronically steerable multi-beam antennas for the payload. So we're supporting all of this with ASICs that we have designed and to provide a full end-to-end system, not just give some components, but pretty much the entire end-to-end system, which means the technology both on the ground from the gateway perspective, similar chips, similar processing, similar antennas, and on the payload as well. So let's first dive into going to the next feature, which is the phased array antenna, which will be the focus of the talk here. So I won't be covering the onboard processing or anything else. This is more around phased array antenna technology and the digital beamforming specifically. So before we go into the digital beamforming, just a phased array 101 for everyone. We all know that a single element, taking again an ideal element, which is an isotropic element, has a certain gain and a certain radiation pattern, which is uniform across the whole space, the field of view. You combine a multiple of these antennas together without anything, just combining a multiple antennas put in a certain orientation, and what you get is a bit more directive pattern. The directivity, basically, as you can see in this, I don't know how, if I can, does the arrow move there? As you can see, the directivity shown by the main lobe here. As you start combining a large number of these, it becomes more and more directive, the system and the antenna. Now you want to, the goal is basically, fine, we got a very nice, highly directive system, but what you want to achieve is to have a full flexibility of moving this directivity in directions that you actually want to scan. So which basically means you want to have a scannable system. You add some phase shifters into the system, which are these smart so-called devices, nothing fancy. All you're doing is basically controlling the phase of each of these elements that you're seeing, which was not the case before. And now you have a very flexible system whereby you can move these the beam in the direction that you want to have. The challenge, of course, are several. I mean, it shows a very trivial representation. It looks like anybody can just bring it up very quickly. The challenges are several with regards to how the system operates. Of course, you have the interaction between these phase shifters and the antenna itself, combining them in a very controlled way, and the frequencies of operation. The larger, the higher frequencies you're operating with, the more are the challenges with integrating all of the system and building an entire flexible, electronically steerable multi-beam antenna. And this is what I've showed is only for a single beam. If you start making a multi-beam system, you need to add a layers of phase shifters dedicated for each of the beams, which is the complexity of the whole system. So if you talk about space is not delivering a single beam solution. It's delivering a multi-beam because it has to be operating over a large geographical area. So in order to move these and have a multiple such beams coming out, or the antenna being directive at the same time to multiple different directions, you need to have a whole level of kind of a replication of these phase shifters for the number of beams you want to support, which means that the whole power, the whole complexity of the system, the swap, all scales with the capacity that you're working with. One of the other interesting thing about the phased array antennas is that it's fundamentally a stochastic average system. What this means is that you've got several sources of noise in the system, from thermal noise, phase offset errors in the phase shifters that we showed, gain errors that you will not every single path will have exactly the same channel gain. You have timing errors, which is more in the context of digital beamforming that I'll talk about it later. So there are so many forms of inaccuracies and errors in the system that, and the noises in that respect, each error is kind of a noise in itself, that they all are actually adding some level of noise into your overall signal to noise ratio, directly or indirectly. But phased array antenna, because it's an averaging, because you have such a large scale, you're essentially averaging all of this out, that in the end, you still end up getting a very beautiful system. I mean, it's when you start building the whole system together, you put the whole math together behind it, it really beautifully comes out. Whatever we had learned in our random stochastic theories back in our electronic engineering courses, you can literally see it in action. All of this theory of large numbers, etc., central limit theorem, everything coming into play here, and the system itself coming out and showing how you can overcome some of these defects. So you don't need to have a very accurate system. You don't need to have a perfectly aligned system that has almost no noise coming or no error coming from anything else. Because of the fact that the phased array system has an averaging impact inside, it basically inherently dials down some of these errors. There are different technological solutions for implementing these phased array, of course. There's electronically active solutions out there, which are, you use analog or RF beamformers, or use a hybrid with a digital. You can have a pure digital beamformer. Or there are other solutions as well that are being worked on, like the passive frequency selective surface structures, like metamaterials and all that kind of stuff, which do some sort of passive beamforming. They could be combined with electronic beamforming to make another hybrid system. So there are lots of various implementations that are being studied or are being researched, but the most mature so far systems are all based on the electronic phased array systems from a design perspective. So we'll take that and dive into the electronic phased array systems. What you see here is a typical analog beamforming at a high level structure. You have a single source of signal that's who's the sorry. So you have a single source here of the digital signal that's coming through, followed by a complete system of RF beamformers on analog beamforming, where you have phase shifters that are connected to the antennas. There are different ways to also implement this. It can be an RF path beamformer, LO path beamformer, analog baseband beamformer. So there are various ways of how you want to go about implementing an analog solution. Generally, the most preferred is the RF path because it's the most power efficient system, but there are advantages of other systems as well. And on the right side is the extreme form, where you take every single path that's coming through from a source and digitize every single path that leads to the antenna itself. This is the classic digital beamforming, where you have a digital all the way, every single path from the antenna. So every antenna element is actually digitized if for the receive or for the transmit, which means you have a multiple A to Ds, mixed signal converters. And of course, you have, depending on architecture, multiple up-down converters in the system to take it to the high frequencies. The hybrid beamforming is the mix of these two, basically implementations, where you have part digital beamforming and a part analog beamforming. You can have a cluster of, or what you call sub-arrays that could be all RF beamforming followed by a digital beamforming. Again, lots of advantages, disadvantages, depends on what you're doing. Like for example, the terrestrial 5G technologies are somewhere between hybrid beamforming and analog beamforming. It depends on the applications and stuff. So they could be doing one-dimensional beamforming on digital, another dimensional beamforming on the RF for the 2D. So what's the advantage of digital beamforming? Why should one go after digital beamforming? As we saw, it's a very complex structure. You have to have analog A to D converters for every single path where you need to digitize every single system. Clearly, there must be some advantage that that provides, and then and what are these advantages over the RF beamforming? So one of the two key advantages that are highlighted here are the first and the third. Firstly, wide signal reception. As you start becoming much larger bandwidths that you want to operate on, so which means like as we talked about broadband applications, when you're talking about hundreds of megahertz of instantaneous bandwidths of the signals that need to be processed, the digital beamforming starts becoming a much better solution because of the very fact that it has a natural, it leans itself naturally to implementation of what's called true time delay, which is a high resolution tap delay line that allows you to combine all these antennas and the signals in the right way that you don't have beam squints in the system. Beam squints are like are similar to a similar analogy, I would say, is like in cellular field, where you have multipath delays coming from different multipath reflections coming from different sources. The signal that arrives at the receiver comes with different delays. If you combine them differently, what you get is a frequency selective fading. In antennas, there's a similar concept. They call it differently, they call it beam squint, but the concept is the same. Basically, it's called antenna selective fading, or frequency selective fading happening on the antenna because the coherent bandwidth of the antenna, which is the delay across all the antenna, is much smaller than the actual bandwidth of the signal that you're processing. So, so you need these kind of high resolution tap delay line for you to be able to combine all the signals of very large bandwidths in the right way. And that's what the digital beamforming offers. In analog, you can do phase shifters, but you don't have delay lines to try and combine them, or programmable delay lines. These delay lines will change with the way you scan. So it's not like a fixed delay line. It's a delay line based on how you scan the system. If you're scanning the beam in lower elevations, you start ending up having a different squint. If you start scanning at a higher, you have to keep changing these tab delays depending on your scanning field of view. Secondly, large antennas. When you start building a very large antenna array, where you start having, again, the impacts of the fact that the antennas are very large and you have to combine all of these systems together, Analog and RF start having their limitations of how you can move these signals across these very large antennas, because RF beamformers are actually moving the signals all in RF and trying to combine them in RF before they with the feed networks and everything else. So for very large antennas, again, digital beamforming becomes important, because your inefficiencies will start showing up even more so when the antenna starts scaling up too large. So your overall efficiency of the antenna can drop if you're not combining them properly, if you're not getting the right performance, or the beam squints start coming into play. Multi-beams, another very, very important part is the fact, how can I drive a single antenna to give, let's say, tens of beams or hundreds of beams that are what the new applications require from the space, including on the terrestrial side. You know that the massive MIMO, as I talk about on the 5G, and similarly phased array antennas for the LEO constellations. Even on the ground, we're already talking about having multiple beams. But for ground applications, 2-3 beams are more than sufficient. But for space application, to deliver a service over hundreds or thousands of devices and cover a very large geographical space, they need to have hundreds of beams that are basically being reconfigured on the fly at a very fast pace. Again, digital beamforming is the only way you can deliver a very large number of beams at a very cost-effective. When I say cost-effective, means from a power and from a swap perspective, size, weight, and power perspective for the payload. Highly flexible system. And the last bit, what it talks about, is decoupling the antenna geometry from the performance. So the interesting bit here is that the antenna is no longer, you don't need to design an antenna to fit your RF profile. You can design any antenna, and the digital beamforming will take care of any inaccuracies of how you laid your antenna out with respect to your PCB routing, with respect to the inconsistencies between you don't have to balance your routing all over the place, because now the digital beamformer is able to remove all of those issues that you had in the system. Overall, basically, it enables the highest capacity and the most flexible system for the beamforming. That's the key message on this thing. The challenges in phased array antenna, okay, so that's just talking about digital beamforming, but there are still lots of inherent challenges. One is that you have to balance the design against various sources of noise, even though it's an averaging, but you still need to design a system so you get the maximum efficiency out of the system. So you have to take care of all the noises and plan out how you want to design this whole array. You have to calibrate every elemental path. Performance, you have to make sure that your performance is not just in certain environmental conditions or certain conditions only. You have to deliver performance across the entire band, across all the environmental factors that are associated with it, which includes temperature. DC power consumption, another very big factor. So it's an electronic phased array system. So which means every element is active in some way. So in other words, you're consuming power for every single element. So you have to drive this power down, or very soon it will basically scale up to become an unrealizable solution. And the design and complexity of the integration, which as you can see from the very nature of the fact that you have so many different components that are getting integrated together. And as you scale up to higher frequencies in Ka band, where you have a 5 millimeter pitch between the antenna, you can just imagine how much complexity is there to integrate this into a single panel if you need to make such a design. The designs need to be scalable, and they need to be able to be manufactured on scale. I mean, basically, it should be mass produced. So all of these factors. So you can make a very nice phased array antenna in a lab, spend days calibrating it and making it work wonderfully. But now you need to make sure that this design can be replicated across a large number of products, so that can be then commercialized. So all of these are big challenges in the system. But for this presentation, I'm not going to go over each of these challenges. I'm going to focus only on the couple of ones, which are the phase noise and the calibration. How am I doing with the time? Yeah. All right, so I'll try and get through this quickly. This is just showing a very high-level block diagram of the system. You have the digital beamforming chip here, which is what we call the prime, which is our chip for the Satixfy. You have multiple analog to digital converters, and digital beamforming that's happening change per of this thing. You have the RF chip that is connected to, and then of course there's an antenna on the top. What it's showing is that there are different sources of noise for the phase coming from the PLLs. So there are PLL sources. There's an RF PLL sitting in the RF. There's a PLL sitting inside each of these analog to digital converters. You have other sources of impacts coming from the noise, such as the thermal noise and the PCB routing, etc. There's interchip routing, there's internal routing. There's lots of stuff inside happening when you start building a digital beamforming solution, which probably may or may not be completely relevant for RF, but you remove some of those, you take some of the advantages, remove some of the impairments of RF, and replace with some new challenges that come from the digital. Two forms of implementation from going from a digital to the RF world. You can directly, you have an up-down converter, so an IQ modulator, where you have an external synthesizer followed by an LO distribution circuit that would then basically up-convert your baseband or IF signal to the actual frequencies of the KU or the KA. Or you have a direct sampling. Satixfy's new chip that we designed for space is a direct sampler. So we go directly into KA band. We have eliminated completely the up-down converter, requiring no up-down converter in the system, but just a simple PA, LNA, and a filter. And we directly put the signal anywhere from L band to the KA band. All right, so what's the big deal about this jitter? I mean, why is that essential? So if you take a signal that's shown here very quickly, an ideal signal, and you and you see, so this signal is presented to the DAC, and let's say the DAC has a clock, which we all are aware of. Everything works on a clock system, which inherently has some jitter present in the system. This jitter translates to an error when you're sampling the system, and that error is represented by this equation shown here. That error is what we all understand as the noise degradation that comes about because of the presence of jitter, which is a function of the frequency you're operating with. So if your carrier was a low frequency, the jitter, of course, impact is less. As you start going into higher frequency applications like the Ka band, which is 30 millimeter wave, or even higher to E band and some of the other ones, you will start seeing the impact of the jitter really becoming more and more pronounced, which is shown here. So what this noise does is basically the impact of this noise in a spectral domain is the spectral broadening of the signal. As you can see, for low band, well, in this low band is the Ku, 14 gig, 30 gig is the K, 50 gig is QV. You can see the spectral broadening that's happening, which starts becoming the bottleneck for your signal to noise ratio in this system. What you see, this one is very quickly the same representation of how the system flows. With regards to the PLL, the block diagram and all that stuff. So it's basically a high pass filter. It's a high pass filter for the reference clock that comes in, but a low pass filter for your VCO, showing the impact of the DAC noise in the system and the PL noise as well. Finally, I just want to show that basically, as you can see here, that how much jitter is required to achieve a low SNR. It's quite a challenging solution. So in order to be able to have a good performance, either you have to invest in a very low jitter solution, which means be very power hungry, or you take advantage of the fact that I talked about that its phased array is basically an average system. So if you can have multiple PLLs which are uncorrelated in the system, then essentially, when you combine this noise, the eventual phase noise that you'll observe in the system will be much lower. The actual jitter will be much lower than what you need to design the system for. That's just talking about the same thing, that you can have multiple ADCs and DACs fed with different sources of PLLs. The challenge there is then you have to synchronize these PLLs across the board so you can have a similar behavior. On the calibration side, I won't go into much detail, but essentially there are various sources of errors that come into the calibration that you're working for. The ones that are shown in the red are the ones specific for RF. The ones that are shown in the blue are the ones specific for digital. Gain and phase calibrations are inherent for all of the phase array, which are common to both. But on top of that, you also have delay calibration for the timing. You need to you have to look after the synchronization aspects between different beamformers. The data converter calibration, so ADCs and DACs, they have to come back in the same initial state every time you turn on the system. And you have a very high capacity digital pipe that's transmitting this data, which means you have these high-speed services that need to be calibrated as well. So all of that basically are the challenges that you need to look at, and digital beamforming gives you the capability to have visibility into every single aspect of these of the components that are there part of the system. That's just showing how the signal flows through different parts and what you end up getting when it goes to antenna, RF, ADC, your up-down converter, if there's an up-down converter, intra-chip, inter-chip is a crazy looking signal which has been delayed through various sources. And at the end of the day, you need to basically able to calibrate this delay, both in the signal, that's your baseband signal, the X, and the phase, which is the part of the exponential part, the phase part as well. So you basically have to do a lot of these phase calibration and delay calibrations that need to meet a certain spec, so that's able to eventually perform as a coherent system. All right, so I'll sum up. So we have seen that basically the communication industry, as I spoke about, is going through a new revolution of and growth in connectivity. Phased array antennas are an important part of this ability for the satcom to deliver the capacity that they're looking for in a very flexible and dynamic way. And there are various ways to implement these phased array antennas, with digital beamforming being one of the chief, let's say, implementation for what the new market is looking for. Having said that, there are lots of challenges associated with phased array antennas, and we touched upon briefly on the phase noise and the calibration bits and pieces. Satixfy is leading this digital beamforming revolution, and we seem to have solved most of these problems. I won't say we solved everything, but seem to have solved most of the things, and it's offering a very compelling solution for the new digital payload. Thanks. I think I was running off from time.
Thank you very much. That was really interesting. I'm sorry to rush through the most complex part of it. To try and stay on time, could we save questions until the lunch break, please?
Yeah, I'll be around, so we can. If anybody has any questions, I can take it up with them.
Thanks.
You.